recording button. I think we can start now. Welcome everyone to the next autumn seminar, Naval Center seminar, which takes place in November, which nearly during the winter time. But the weather outside is very nice. Before we start, I would like to ask you to post where actually you are, because sometimes it's good to know where you are placed for us to know. I'm in Leeds, maybe someone else is in other place. And the reason why, because I would like to welcome everyone to say either good morning or good afternoon or good evening, whenever you are placed now. So I'm placed in Leeds. So if you can put where you are now. So Paul is in London. Nick, I think, is somewhere. Oh, Kuwait. Brilliant. I'm wondering what time is it in Kuwait. So again, welcome everyone. Today's agenda is as follows. So I will do the very introduction of the Naval Center and welcome everyone. I will then introduce our amazing speaker, who is Paul Edwards, but I'll introduce Paul Edwards in a second. And then we're expecting end of the seminar at 3:30 British time, maybe a little bit earlier. So my name is Michał Drewniak and I'm a lecturer in civil engineering at the University of Leeds. Also, I'm a co-director of the Naval Center of Cement and Concrete Excellence. What is the Naval Center? So Naval Center, I hope you can see my screen. Can you confirm whether you see my screen, please?
Yeah, no problem.
Yes,
no problem.
Perfect. Okay, so the Naval Center facilitates solutions for both industry and academia.
Sorry for interrupting, Matthew. No. Michael, sorry for interrupting. My keyboard stopped working. I'm just coming back. I have to restart the system.
No worries, that's fine.
I'm coming back.
So the Naval Center facilitates solutions for both industry and academia in cement and concrete design engineering. It focuses on developing links between current material experts work at the nano and microstructure scale and those focus on the long-term micro-scale design performance, enhancing both traditional and innovation-led design. So the Naval Center, we organized every other month seminars, and today is one of them. So in spring and Easter seminars. Seminars. And we also host a RILEM ICT CPD's bio every other year, seminars. Hopefully we can get more and we can create it. We can have more often those seminars. And also every year we are having an annual Naval Center Symposium and a national PhD competition. This year took place 25th of October. And next year we can expect this competition and this symposium in the similar time or in December, just like a couple of years before. We have our website, so feel free to visit our website. It's on the University of Leeds domain, and also if you like and if you wish, and I highly encourage to follow us on the LinkedIn. We are Nick, who is here. He's posting a lot of different very interesting things on the Naval Center and on the different meetings or events that are related to Naval Center. So feel free to join and just to feel free to follow LinkedIn profile. Now I would like to introduce our speaker, who is Paul Edwards. Paul Edwards is a regional director for BG&E in the UK and Europe after working with the Arab as a structural engineer for 25 years, where he was heavily engaged in many adaptive reuse projects. Paul joined the BG&E in January 2024 to lead the company's efforts here in the UK. In the UK. So I would like to welcome Paul. Thank you so much for being with us. Paul's presentation would be on materials reuse approach adopted by BG&E when delivering the Quay Quarter Tower project in Sydney. From the housekeeping announcements, please keep your camera and microphone off until the Q&As. If you have questions during the seminar, please feel free to put your questions in the chat. We are going to answer those questions in the Q&A session, which will be just after the presentation. Today's seminar is recorded, so the recording would be available if you like. We are going to share the link for the recording. And this is CPD certified seminar. So if you like to, and if you wish to get the certificate, feel free to contact Neville Centre at leeds.ac.uk, and the certificate will be sent to you directly. I think I don't have any other announcements. So Paul, feel free to share your screen, and thank you so much for being here with us, and the screen is yours. Thank you.
Perfect, thank you. So can everyone see the beginning of the presentation?
Yes, we can see the presentation.
Excellent. Well, thank you for hosting me, Michal. It's a pleasure to be virtually here. And yes, let's see how we get on. So there we go. I was just going to give a brief introduction to who BG&E are, because BG&E are an Australian organisation primarily, civil and structural engineers, quite mature in Australia, but with only relatively recently, since 2016, in the UK. And this is the image to the left, is part of the completion of the Sydney Metro line, this particular station being at Barangaroo, which is near where BG&E's office is in Sydney. So BG&E are 100% employee owned, just over 1,000 staff, and were founded in 1970 in Perth in Western Australia. And as you can see, very Oceania-centric in terms of offices, but a gradual reach out further west. And in London, we are about 55 civil and structural engineers with a small facades team. We cover a wide range of, let's say, disciplines associated with civil and structural engineering, and that's growing as our own project base grows. But for the Quay Quarter Tower project, those disciplines that are highlighted were the primary ones: the structural engineering, construction engineering, and the materials and durability. So, what is Quay Quarter Tower? A bit of project background. This is a view of Sydney from basically the north shore of Sydney Harbour looking south. You can see the Sydney Harbour Bridge off to the right. And Quay Quarter Tower forms part of the skyline of the central business district. You can see it there. The overall project was delivered between, I think BG&E started working on it in about 2017, 2018. It was completed in 2022. About £600 million capital cost. The project was working with AMP Capital, an insurance and general asset holder in Australia, with Multiplex as the main contractor, and the architecture developed by 3XN, along with our local executive architect, BVN. And you can see some project stats of the completed building on the right. So 250 meters tall at its completed state, 51 stories. And the project ended up adding about 40,000 additional square meters to the footprint of the building, whilst retaining 70% of the existing structure. Now, the existing building was completed in 1976 as 50 Bridge Street, always for, in effect, AMP Capital, so always for the same client who'd then operated it for following 50 odd years. And you can see more or less the difference between the previous building and the now new building, to give you some idea. So the existing building, what was stroke is it? Because most of it's still in place. So the building was designed by an Australian practice called Rankin and Hill in the late 1960s and early 1970s as a 46-story commercial tower, again for AMP. And the structural form was a rectangular in situ concrete core with perimeter columns, in situ beams spanning between the core and the columns, and the floor plate constructed from planks with structural topping. Just some images to show you the condition of the existing building once the soft strip had been undertaken. First site. So these, you can see the downstand beams, you can see overall floor heights, giving an impression of those quite tight. Areas where some coring could occur to allow for services to pass through. And again, the further details are showing where the precast planks landed on the in situ beams. Some areas were double height to allow for an atrium. But overall, and then at the upper level, there was upper levels had some steel work with some metal decking, floor slabs with some. You can see some mild water ingress, but given the life of the building over 40 years, nothing particularly significant. From those photos, I think one might take the impression that the overall condition of the building was reasonable. Didn't seem to be any significant signs of distress. We'll go into some of the findings as we get through this. So the original construction, now maybe when we're constructing buildings like this, we might be pumping concrete a lot more, but the actual tower itself was built using a kibble bucket process, example shown to the right. And the other interesting element was that the core walls changed both in design strength of the concrete, but also in moving from normal weight concrete towards the bottom to lightweight concrete towards the top. So you can see that there's a change in materials, and all of this would have been constructed with the use of a kibble bucket rather than pumping or anything else that we might be doing at the moment. A bit more about the project concept that just feeds into then the work which went into achieving the 70% retention of the existing. Oh, there we go. So just the original building built, the grey area in the second image you can see is the area that was demolished, and then the blue is the reconstructed area. Just helps to visualize the proportion that was both retained and then the scale of added floor area. That the goal of the project, as well as increasing the floor area, was to give the building an additional 50 years of design life, and the retention involved extending the core. So I'll talk a little bit more about those two things as I go through. And again, just a time lapse. It's a nice little image just to share of, not really a time lapse, but just an image of this overall project. That's just to visualize it a bit better. And I'll talk a little bit about some of the details about how we achieved that. So, existing building investigation. So there was reasonable existing building information in terms of drawings available, but we went through and took full 2D surveys of all the floors, all the building, and also undertook 3D point clouds. And that I'm not going to go into a lot of detail about this, but this survey information was used to help us develop an existing building model, which we used to develop and generate construction sequences and building movements. So it was quite an important first step to gather all of this information for what we then utilised it for afterwards. And I'll show some of that towards the end. So a lot of the work was to do, if you were going to keep 70% of the existing structure from a building built in the early 1970s, a lot of the work necessary was to try and understand the condition and capability of that existing retained material. So a lot of effort went into understanding all of that. Now, typically, I'm sure we all know, characteristic compressive strengths are, for a new build, we do using cubes or cylinders of the concrete mixes that we've specified when they get brought onto the site. Obviously, in an existing building, that concrete's already there, so you can't have material you've taken from the concrete that's there to be poured and store it on one side in relevant conditions and then test it as you go through. So that material's already there, and you've got to try and understand how close to what it needs to be it actually is. And there are various, at the time when this was undertaken, some of these standards have moved on, but there were various standards which were potentially available to the designer to understand what the existing strength of the material was. So the design team evaluated these 4 codes for assessing the existing material and tried to understand which one might be the most suitable to follow without necessarily wanting to choose one in particular, but having evaluated all 4 of them, the consideration was that the approach generally outlined in ACI 214 was the most relevant. This being because the other standards just didn't quite, and the reasons are there on the slide. I wasn't planning to read them out, but it was felt that the ACI 214 approach offered the most sensible way of harnessing the existing concrete information gained from site investigation. And so a starting point for a lot of this was to do large amounts of non-destructive testing using Schmidt hammer. This enabled a relatively rapid understanding of the overall building's concrete existing condition, and then therefore enabled areas which were potentially below desired strength to be identified. So here there's a graph which just shows Q value on the left is in effect a shorthand for the compressive strength of the concrete at the various floor levels which are along the bottom axis. So you can see that there's a zone indicated by the Schmidt hammer testing around the mid height of the building, which potentially isn't quite at the desired concrete strength that the design would require. And therefore, having identified relatively quickly an overview of what the concrete compressive strength in the building was, by having that Schmidt hammer testing data, it was possible to then focus destructive testing. So representative concrete core samples were taken throughout the building, and I'll go into some further detail about where further concrete cores were taken following non-destructive tests to indicate areas of potential weakness. But these cores were taken both to calibrate and then to further identify low strength areas. And you can see that, again, if you cast your mind back to that Schmidt hammer test, this is again for core walls, you can see that the further detail provided by the destructive testing bore out the higher level information found under the Schmidt-Hammer testing. And the black line is the design strength of the core wall. So anything below the black line as an approach following the ACI 214 method be an area of concern and need for intervention. This approach in general was adopted for all structural elements. So concrete columns were assessed, and you can see in the table on the left the original design requirements for the concrete strength, and you can see in the table on the right that actually determined by the investigation. And generally, as far as the columns were concerned, either at or above the original building's desired material properties. Same story for beams and slabs. Generally, the existing material in the beams and slabs was found to be above minimum requirements, in some instances by a fair margin. But in terms of the cores, that core wall of which the whole core was retained, that story sadly wasn't carried through. And it's worth bearing in mind that all of this comparison with the original design strength is before any of the changes in load due to the new, taller, larger scheme come into effect. So the investigation into the existing building revealed that actually the in situ strength of the material was below that identified as being necessary in the original design. And you can see in the chart everything below the black line, all those red dots below the black line, the F-C, resulting again from the ACI 214 approach, being areas where the concrete wasn't at the relevant level of strength. So the implications of that were relatively significant. Zone in the mid-height of the building, where there's the compressive strength of the concrete isn't up to scratch, knowing that we're then going to add another 5 stories to it and increase the floor area with the associated increase in wind loads, for example. Quite a significant finding. What then did we do? So it's worth bearing in mind that the first pass of all of both the non-destructive and destructive testing were done on a representative manner. So you're talking approximately around, in terms of Schmidt-Hammer, 10 to 12 tests per wall, and then in terms of the cylinders for destructive testing that were taken out, maybe 1 or 2 on each floor level. The decision was, if we'd have just left it at that in terms of trying to understand the existing material, the resultant costs to the project of reinforcing the core walls to achieve the desired strengths of the new build project would have been significant. You'd have been talking about 15 stories where each core wall would need to be strengthened either by steel jacketing in most instances, and maybe also where tension was an issue in carbon fiber plating. The costs of that would have been tens of millions of Australian dollars, which is quite a large increase in the overall budget. So the decision was made to undertake a much deeper assessment of the existing concrete walls to try and understand exactly what the minimum level of intervention would be to achieve the desired overall strength of the existing core. And this table starts to pick up some of that more detailed investigation where you can see some of the identified destructive core strengths developed and starting to focus down a lot more on just a couple of floors rather than a group of 10 to 15 floors. And again, so this is a similar repeat to the graph before, but with 3 more rounds of testing added to it. So just justifying further the areas where interventions might be made, and again honing in on those levels in the mid above level 25, where significant intervention might still need to be made. And this comes back to some of the survey information, but in parallel to all of the investigations that were being undertaken, the overall design of the project was progressing, and as part of that, the structural engineers built an ETABS model of the existing building as a starter, and we're using that model both to understand the existing stress and strain and compressive loading of the building in its existing form, but then also to understand what the implications would be through the interventions proposed. And this information, you can start to see the stress and plots for compressive stress and shear stress on the core walls, expressed as an unfolded envelope. And this helped to comparing this to the Schmidt-Hammer testing and the destructive testing, helped to understand where weak concrete combined with areas of overstress. And as we work our way up the building, so that first slide was level 3. This, for example, is level 16, starts to be some areas more where stresses are increasing, and the design, the actual applied design stress in the building, you can start to note in the top left. Again, certain areas, level 21, the areas in red cloud are where an intervention is required rather than it being acceptable or on the verge of acceptability. And then you get up to levels 27, 28, where in effect, for some reason, the whole core wall is not performing well. Now, why was this? I think having spoken to the team who delivered the project a few years ago, the consideration was really to do with the method of construction and the fact that that kibble bucket approach is, although commonly used at the time and still is used now sometimes, depending on the scenario, it can be harder to ensure the quality control of delivery of the material, and then obviously compaction and everything else. So there seemed to be, I don't know, someone was having an off day when they were pouring levels 27 and 28, where consistently the concrete supplied in the building was poor. So you can't easily see because the red cloud is hiding some of it, but the actual compressive stress limit identified from the testing for this floor level was under 5 MPa, which is very weak. Associated with that may be the fact that it was a lightweight concrete mix too, but that's fine. There were some other issues which were found due to the non-destructive and destructive testing. So the perimeter columns were formed from elements of precast concrete, which were then infilled. Well, I say infilled, but one common area of concern that was found was actually the infilling of the precast around the columns wasn't undertaken very well. So there are large numbers of column voids found, and you can see some images here of the nature of what was actually found. So this was discovered by undertaking a small drill into the precast concrete and then finding that there were voids. And then once the voids were found, then it was decided to saw cut off the one face of the precast concrete to understand the nature inside. And you see what you can see here. There's obviously been issues in pouring and compacting well the concrete, leading to significant voids in the precast column molds, which is obviously not desirable. And this was simply rectified using, in effect, a concrete replacement for the new columns and then covering them up. So relatively simple once you've understood that the issue's there to resolve, but it's worthwhile just as a note for anyone engaging in any adaptive reuse or existing building survey where there may be elements of precast concrete to one think maybe whether that precast is there just to achieve an external finish and is hollow. And if that is the case, then maybe the internal is worth trying to understand as well, because there may be voids due to how that element was constructed. And the team, given that one of the requirements on the design team was to justify the building for a further 50 years, that meant that it was necessary to understand not just the condition, but also how the building was constructed and to understand how close it was both to the requirements of the incumbent design code at the time of its construction, but also in relation to what would be now considered relevant 50 years on. And so the team undertook assessments of the existing reinforcement, both to understand grade, but also to understand spacing and lap distances. And this was done using calibrated cover meters for columns and cores, and generally one or two areas, but generally everything was found to be acceptable and in accordance with design standards as far as that was concerned. And also it was necessary to assess carbonation rates. We want to keep the 70% of the building for the next 50 years. You want to make sure that the concrete's still active in terms of protecting the reinforcement. And these two charts, on the one on the left, carbonation for the columns, no, obviously the precast and the internal environment in which the majority of the columns were meant that there's hardly any, practically zero progression of carbonation. Slightly different in the core walls on the table to the right, where the majority of the carbonation, predicted carbonation, were after 100 years, bearing in mind it's 100 years because effectively 50 years in terms of the existing building and want to justify it for another 50 years. In general, within the concrete cover depths of the existing, apart from some small areas toward in the basement levels. So you can see that third row, UBW2, where the intervention proposed there was again just a traditional concrete cover replacement for concrete repair to locally achieve the required design life later on for those areas. And then also chlorides and sulfates were tested for, and even despite the building being adjacent to the Sydney waterfront, no significant chloride ingress noted, and no really significant sulfate ingress noted either. The rates of sulfate ingress were thought to be due to the actual original concrete mix rather than any atmospheric ambiental effect. So given that nature, given that information that was found through the testing, what actually happened, so just to take you back a bit to the actual existing building. So on the left, you've got the existing building floor plan with a typical floor plate, and the project also keeping 2/3 of that floor plate and then demolishing in the dark grey on the left. one portion, and then on that same side, which is the north side of the building, extending out the core in dark blue, which you can just see here, and then obviously extending the floor plate as well. That you've got the whole conversation around time. One of the key considerations of this building is actually a time, a chronological understanding, because the existing concrete has done the majority of its shrinkage and its creeping under the existing loading, whereas the new material that's going to be put in there is all of that journey to go. So how do you manage that? And then the other act of intervention, you can't see it clearly on this floor plate, but you can, was basically at certain floor levels, this blue floor plate was wrapped around it's not quite here, similar to what you can see here, but more profoundly, was wrapped around the existing floor plate, basically every 10, 15 floors to grab onto the full core of the building to help resist with lateral loads. So there's quite a lot of interface between new concrete and existing concrete. As noted, that new concrete moves, and because the loading on the building changed, the existing core the building had a larger floor plate with some significant cantilevers off to one side, which weren't there originally. So the distribution of tension and compression in the existing core also changed. And how was that dealt with? That was that connection between the new core with its shrinkage and the differentials in creep between the two, was dealt with by constructing a pore strip between the two. And this basically was all the way up the height of the building, over 2,000 steel dowels, going into the existing concrete, and then connecting, allowing a pore strip to then be put in place to the new areas of concrete. So that pore strip was left out for 56 days before it was then cast up to join everything together. Throughout all of this, as I noted before, a comprehensive analysis of the existing building and then the new building was undertaken using CSI ETABS. This was in effect a 4D approach, so also included time-dependent assessments, just to fully understand the movement and behavior of the building as we went through all of this, and making full use of the knowledge of the existing material properties. So this resulted in this model, which hopefully you can see here, of a 4D assessment, whereby we modeled the building from its original construction, modeled it in service for the length of time before it came along, and then modeled its demolition. Just run that again. And then modeled the reconstruction. So you can see the stages being built. You can see under loading, and then you can see it being demolished as agreed with the contractor, and the final steps, and you can see the elements being added in all the way to achieve the new building. This is a combination of all the existing survey information that went into this, so all of the material properties understood and the geometrical properties understood from the survey went into building this model. Really key to then successfully develop the overall project. You can see on that section on the right, where you've got the new building light blue and the existing in grey, and an indication of some of the issues which were there to be developed, but in effect, time and movement. This modelling enabled us to provide a series of presets to achieve the construction successfully, which is good to show. And then also we were able to model lateral movements too. So again, you've got the same construction going on, but here construction sequence going on. You can see how the building, when you take load off it, behaves, and then how it behaves when you put the load back on in a different way. So existing building being constructed, start to demolish it, the building moves, start to rebuild it, and the building starts to come back again with the additional load and the cantilever. So all of that movement needed to be understood. And again, I'll just reinforce that it's not an immediate thing. It is heavily time dependent. So needing to understand the nature of the material and the shrink and creep behavior over time, but also during construction, very important to enable accurate construction to be undertaken. Worth noting that this building had a number of issues, some of which I've touched on. It could have been an argument to start putting forward try and demolish the building or even significantly or in total. I think it's credit to the client, AMP, that they were really keen to move in the most sustainable way that they could. And these are relatively high level numbers, but you can see some of the impact that decision made. I think the significant saving in carbon, but also worth noting that the significant saving in construction time and therefore on overall construction cost. So the client's decision right early on to go down this road without any of this evidence in front of them, fortunately paid dividends. And this is, just to finish, this is just a time lapse of the overall process in actuality. So this is all of the protection going up pre-demolition, and then you can start to see top of the building coming down, but also the left-hand side coming down. The remainder, it's the cladding having been taken off, and the new cladding starting to be put back on, as on the left-hand side, the new build elements start to be erected. And you can note the relatively large cantilever that goes further and further up the building. And there we go, completion. Now, I didn't say how, after having gone through in a little bit of detail, how the core walls were found to be significantly weaker than desired, and how this building, as you've just seen in that time lapse, changed significantly, leading to significant changes to the lateral load on the building, how those areas were resolved. What happened was that for those two key floor areas, levels 27 and 28, they were identified as needing steel jacketing reinforcement. So they're basically steel plates applied to those core walls, but only on levels 27 and 28. And if you take your mind back to where the initial investigation revealed that maybe 10 to 15 floors might have needed that level of intervention, I brought that down to only 2. It's quite a significant saving. There were 28 walls that needed tension strengthening down towards the bottom of the south face of the core. This due to just the change in loads due to the new profile of the building. So you, again, take your mind back to the 4D model where the loading, I'll just go back a couple of slides so you can see it. On this left-hand side, you see the building being unloaded moving out to the right, and then as it's loaded up again, moving out to the left. So the base of that red core starts to be put into towards a permanent tension due to the redistribution of the loading, the static loading in the tower. So there were 28 walls tension strengthening using carbon fibre. And the other elements, which I didn't really touch on in much detail, were the link beams, the coupling beams, and the core. There are 125 of those, which, after, again, relatively detailed material assessment, it was decided to strengthen those using a mixture of steel jackets and carbon fibre for the compression and tension faces, respectively. So I think that's, in summary, the work done from a materials perspective, primarily on Quay Quarter Tower. The project was highly commended and awarded several recognitions by CTBUH a couple of years ago. I think it is still maybe the largest adaptive reuse in the world. I mean, that's quite a grand statement, whatever. It's a great exemplar of what we can do with our existing building stock, and maybe how we should think about reutilizing a lot of the buildings that we have out there, and some of the things we might need to think about when we do. So thank you, and if anyone's got any questions.